All right, thank you everyone. We'll get started on time because I have a lot of content to cover and I don't want to tear out of the time slot I had allotted. So my name is JF. I work at Apple on Client and LVM. I'm also in the C++ committee. I newly became the language evolution chair. So what's everyone's favorite C++ keyword? Volatile, thank you. Register, yeah. Const expert, okay. I'll have a few of these in the slides, so I'll try to cover everyone. But today, the main point of this talk is to talk about Volatile and how I'm trying to deprecate parts of it inside C++ and inside of C. So what I'll cover is just how does it get started? Why does it make sense? How can you shoot yourself in the foot with Volatile? There's many foot guns in C++. Volatile is one of them. What does it actually mean? I'll try to cover what we think it means, what it actually means in the standard, and what that translates to for compilers. And you'll probably be disappointed in a lot of this. And then what's going to change? So first, how did this get started? Well, if some of you were in my talk last year at CppCon, I talked about signed integers or 2's complement. And in there, at the end, very, very end, I had a slide because I was trying to deprecate 2's complement, right, which is in C++ 20. And I had this slide that says what's next. And then if you look here, so these are kind of jokes, kind of not really, but kind of. And I have this slide here that's like the next last bullet point where I said deprecating volatile. And everyone thought it was a joke. But I actually had written the paper to deprecate parts of Volatile already and got published like a week later. So some of this, like, if you care about these things, just watch out because I might deprecate the rest. Yeah, so I had this slide and basically I'm kind of going through the standard and seeing what doesn't make sense anymore. How can we simplify the language to remove a lot of the weird corner cases and stuff like that to make the language more usable and have fewer sharper edges. And it actually started for me like 2 years earlier at previous CppCon talk where I was talking about atomic optimization. So I had a section of this talk about Volatile in particular, right? And basically I kind of went through what it means really quickly and was like, here's what compilers do with it, but I don't really know what it means all that much. I had a good idea, but it's actually quite confusing. And I go into depth of like what compilers do and stuff in that talk for optimizations purposes. But for me, the reason I wanted to talk about Volatile and try to remove the sharp edges is because I've seen a lot of bugs related to Volatile, like a lot of them. And when you use Volatile, you have good reasons usually, right? You can be misguided in using Volatile, but most uses of Volatile that I care about aren't the misguided ones. It's the ones where like you're doing something that needs Volatile and you're doing it wrong because it's hard to do properly. And specifically, say you're shipping hardware, right? So you have like really low-level C or C++ code that goes into hardware and that's like burnt into a ROM that you can't change after the hardware has shipped. If you have a bug in there, you're kind of like, you can't really do anything. It's there and like you can't do anything. And the hardware, presumably you tried it out, it seemed to work. But maybe there's something unintuitive that was happening or whatever, and that Volatile that you used or misused has a bug that you don't notice until you ship the hardware, then you have to like, just do new hardware, right? So it's not a great thing. And then when you try to use volatiles, there's plenty of nonsense in there, just like on this slide, right? Like, what does it actually mean? It's kind of weird, and I'll try to give you examples of that. So what I did is I kind of collected my ideas, talked to a bunch of people, and I wrote a standards paper. The standards paper is really long, because I tried to go back in history and figure out, hey, what does that actually mean, and other stuff like that, and what could we do? So in there, I lay out, here's what I think doesn't make that much sense, and I asked the standards committee, what do you want to do with this? Right? Like we have all these things, could we try to tackle them one at a time? And I lay out a bunch of ideas of what we could do and try to plant seeds of like, well, maybe other people want to do other things there or there. Like there's stuff that doesn't really make sense in a bunch of places in standard. So what I did in that paper is I had a few motivating examples for stuff that doesn't make sense with Volatile. How do you misuse Volatile, right? And I call them motivating examples. It's really kind of demotivating examples, I think. Because you look at it and you're like, what is that? And you think about it and you're like, oh, this is kind of weird. Why is this in the language? So let's get started with that. So I have this example here where I have a struct with 2 nibbles, right? So assume 8-bit per byte as every machine is these days, right? We should deprecate any car bit not equal to 8. But ignoring that side thing here, I have 2 nibbles, right? 2-bit fields, and I declare the struct as a volatile thing, right? Now I write this code and I go in and I set the first nibble to 3. Now the whole thing is volatile, but I set to only touch the bit field. What does that mean? Well, it's kind of weird. So am I going to load from the second nibble? I don't really know. Am I going to store to it afterwards, I don't really know. And that depends on the platform. And so it's kind of really not well defined. And if you look at what LLVM does, in fact, there's a code review open right now where in the ARM calling convention, there's a bug in LLVM with respect to volatile bit fields. I don't know that it matters that much, but it's really weird. And when you're talking to hardware, volatile bit fields are actually a thing. Right? So if the compiler gets it wrong, or if the programmer gets it wrong, because how many of you know what this does? I certainly don't. Then like there's actual hardware bugs, right? The hardware manual will say you should touch like these parts of the hardware this way, and I don't know if that does it. I don't know if the compiler does it properly. So that's kind of unintuitive. So that's one example that I have. Like, this is weird. Maybe we could have something better. Here's another example. Kind of the same idea. Two nibbles. One of them is volatile. The other is not. Right? What does this do? Right? Like if I access the non-volatile thing, can the compiler touch the volatile one? Well, most hardware does not have a way to do bit addressing. Right? There's a few hardware that do, right? Specifically for accessing hardware, it's possible to touch individual bits. Most hardware doesn't do this, right? So there's literally no instruction that will allow me to access only the non-volatile nibble and not touch the volatile one. Right? So that's kind of weird. Here's another example that's a bit weird. I have a union, right? And this union has a car and an int inside of it. Now, in most targets, the car will be 1 byte, the int will be 4 bytes. So it's kind of a lopsided union. Now, I come in and I try to access it when the union is volatile. What does that do? Well, if I store the character, am I storing just 1 byte or am I storing 4 bytes? I don't know, right? If I copy the union, do I need to know which of the union's members is active to properly copy it, right? So if the rule is, if it holds a car, you move the car. If it holds an int, you move the int. Well, if I just do like union copying without specifying which member I copy, do I need to copy the active member now? So does the compiler need to track which member of the union is active, just like on std variant? I don't know. That's kind of weird. Here's another weird thing. I have a volatile int and I increment it, right? So increment usually is a load, a modify, and a write. Right? So you might think, well, this just uses read, write, modify that my CPU has. Maybe, I don't know, right? Or does it do a read, semicolon, modify, semicolon, write, right? So you could get like an interrupt in there, your process gets swapped out, and then you come back and something like that, right? Like, I don't know what this does, right? So is it equivalent to this, right, where I have a temporary, or is it equivalent to an atomic? And same thing for pre and post increment and stuff like that. It's kind of weird. Another weird thing, I have this example here where I have 2 integers and 1 volatile variable, right? And I do I equals volatile equals j, right? Now, does this store j into volatile, reload volatile, and store it to I? Or does it do this instead? Is it allowed to say, well, you took a non-volatile thing, so of course it didn't change, and I copy it through? And compilers kind of disagree on what this means. So that's kind of weird. Here's another weird thing. I have a really big array, right? There is no hardware, if you know transactional memory, that has instructions that can do one single store for this. It's a very, very big array. And I'm writing C code right now, I create a volatile atomic of this struct, right? Now, atomic means usually you can't tear, right? Like the thing doesn't break up, but volatile usually means it is allowed to tear. So what does it do when I copy into this, right? What does that actually do? Well, in most implementations, when you have very big atomics, to pretend that you have sequential consistency, if you do stores or loads that are bigger than the instructions your target has, the compiler has a sneaky lock or a set of locks that it'll acquire behind your back when you do these instructions, acquire the lock, do individual stores, release the lock, and go forward. Now with volatile, it's kind of weird that you could write volatile stuff and it acquires a lock. That's kind of unexpected, right? Same example, but with std_atomic this time. Std_atomic supports volatile qualification. I come in and I say, hey, I'm going to do a compare and exchange. Now, volatile, as I'll explain later, usually says you can only touch the bytes of the destination once, right? So if you put a store, you're only allowed to touch them once. Well, compare and exchange, most of the time, can fail, and it can fail spuriously. So not even like, I had no other threads writing to it, therefore it cannot fail. It might fail even if nobody else writes to this location. Right? So that's kind of a problem, because then I'm saying, well, do a volatile compare and exchange, and I have no idea how many times this gets touched. There's a separate code review in LVM that I saw this morning where someone was like, this is a bug in LVM. And I don't think it is, but like LVM can actually touch the bytes of a volatile location more than once if you do a compare and exchange. Right? So that's kind of unintuitive as well. Here's another example. I know what this means, right? So does everyone understand this code? Right, so I have a volatile int putter. Right? If you want to do a quick translation, it's just volatile west for the other thing, right? Now, I thought before doing this talk of ordering the little bracelets for volatile west and volatile east and giving them away, and then I forgot to do it, and I thought about it like earlier this week. So cool story, but imagine you have bracelets for your favorite volatile west or volatile east from the rest of the talk. But so this makes sense, right? Like what you're saying is you have a pointer and the destination you're pointing to is volatile. That is good, right? Like you can write this with volatile, that's fine. Now, what if you do this, right? So if you have volatile int without a pointer or anything like that, what you're doing here is you're using a top-level volatile qualifier. What does it mean? Well, depending on your calling convention, right, things either pass through registers or pass through the stack. Does volatile int force this to pass through the stack? Because there's not really a thing as a volatile register, right? But does that mean that it needs to pass through the stack? Does it change the calling convention? If it does pass through the stack, you have to store it and then load it back. It doesn't mean that on the destination side, you're only allowed to load it once, and you have to load it once. Well, what it actually means in the C standard is nothing. This means nothing. This does not change the calling convention, and in fact, you can forward declare and declare the same function with or without the volatile qualifier, and they are literally the same, right? And in C++, they mangle exactly the same, because the volatile means nothing, right? The reason this is there is because this was the rule for const, and when C++ started growing a bit more things, they also added volatile, and for consistency, well, the volatile also has that semantics. Now, one could argue that the semantics for const makes no sense, but the semantics for volatile are consistent, so at least we're consistent. That's good. Next thing, same thing, but with the return value, right? Now, spoiler, it's the same thing. It doesn't mean anything, right? But like returning a volatile thing is kind of weird, right? Does it need to go on the stack? Does it go in register? Whatever else? It doesn't do anything, right? It's literally the same as not having volatile in there. Now, because this is a C code example, I have the little void in parentheses just to trigger people. It's good. So another thing here is, well, volatile is really for hardware. So what you're thinking is, I'm going to write abstractions around volatile. So you go and you make a class, because it's devices, and then you initialize the register that's in there, and then you declare it volatile. Well, that doesn't actually do anything, right? Because C++ says that when you have a constructor or destructor, volatile does not apply inside the constructor or destructor. Why is that? Well, it's consistent with const, right? Like when you write when you have a const instance of a struct or a class, const doesn't apply in the constructor and destructor because you kind of got to touch the bits, right? So volatile doesn't apply here. It's kind of weird again. So consistency again in C++ is not always great. Here's another example. I have an external volatile int somewhere, right? There's an int somewhere that's volatile, and then I have a pointer to it, right? Now I'm going to go in, I'm going to do this code, right? What does this do, right? Does this emit an empty function that just returns, or does it load the volatile value? Anyone want to take a guess? It loads it? It should load it. So this changes behavior based on which language you're using and which language mode you're using. So if you go on math.com, Godbolt, sorry, and you write this, and you write it in C, it'll do the load, but if you write it in C++ 03, it won't do the load. But if you write it in other versions of C++, it will do the load. So the standard has flip-flopped around this quite a bit. And in fact, Clang has a flag to support the old weird behavior or something like that. So, and like, I've talked to users who've written that code expecting it to do something. I don't understand why, but they expect it to do something, right? Come on, it makes no sense, right? But yeah, it's valid syntax. Maybe it needs to have a behavior. I don't know. So let's dive in a bit. I explained a bit what I thought stuff meant, but what does volatile mean? Just kind of colloquially, like between us, right? Just don't tell anyone else, and YouTube, stop listening, please, right? But like, let's just talk about what we think it means, right? And I've gone and talked to a lot of low-level hardware people. I've written some amount of low-level hardware stuff, but you know, I want to make sure that when I talk about volatile, I actually understand what people expect from it and what the intended design for it was. That's what I'm going to do right now. So, knowing your own ignorance is the first step to enlightenment. Hiram, that's your little poetry for you. So, first thing that people usually think that volatile means is just optimizers, just like kind of back off a bit, right? So what people expect is like, well, the compiler should back off and not do too much, right? So if the source code contains a load or a store that's volatile, then those loads or stores should occur, right? So if you wrote a load or a store, they should be there, right? You expect them to be there. So also, if I write a load, you can't just remove a subsequent load that's to the same address, right? So if I load a volatile variable, load the same thing again, you can't assume that the value is the same, right? That's an expectation. You can't really speculate it, right? So you can't move it out of the branch, even if you know the address is valid. I don't want you to speculate it. And you can't like speculate, then undo the thing either, right? So that's an optimization compilers do sometimes. We'll speculate a thing and then undo it. In very specific cases, you're not allowed to do that. So that's one thing. Just like back off, don't touch stuff too much. Now, one thing that people don't really realize about volatile, well, not everyone realizes, is the memory can tear. Right? So what I mean by that is you do a store, another thread reads it, or you have an interrupt that happens while you're doing the store. It is allowed with volatile in every case that the store doesn't occur in one full, you observe half of the store basically, right? So this will happen, for example, if you don't have a store instruction big enough to express that store, but there's also instructions both on x86 and ARM and other architectures that actually in the microarchitecture are equivalent to 2 stores, right? So it means that another thread can observe half of the store occurring, right? So it's not atomic in that sense. So this is allowed by volatile. It's not a property that everyone wants, but a lot of people know that this is something that volatile does not guarantee, right? So it is allowed to tear. Does that make sense? Another thing is it guarantees some instruction ordering. Paul, no, I don't want your questions. Paul McKinney, no. At the end, especially for you. So one thing that people expect for volatile is it guarantees some instruction ordering. Right? Now, people don't really understand what instruction ordering guarantees, but they agree that, like, say you do volatile operations one after the other, well, the compiler can't reorder the instructions, right? So if you look at the assembly, the instructions have to be in that order. Right? Now, can you reorder non-volatile things around volatiles? That's not really something people agree on. We'll talk about that a bit later. And it also doesn't mean that another thread will observe the instructions you execute on one thread in the same order, right? So, because hardware doesn't guarantee this, right? So it tries to guarantee that the instructions that get emitted will happen in that order, but it doesn't really guarantee that they'll be observed in that order, right? Because it doesn't guarantee any synchronization, right? So per the standard, it doesn't guarantee synchronization. Now, some compilers decide that it does guarantee synchronization. Hi, Billy. But it's not guaranteed by the standard. Some compilers decided to be nice, and that's kind of a mistake. So MSVC does this for x86 targets. Extensa does this as well. I talked about it a bit more in my previous talk about optimizing atomics. But generally, when you write volatile, you're not writing atomic, right? It's different words. Another thing that volatile totally guarantees is some implementation guarantees, right? So volatile says, like, hey, like implementation, just let the programmer know what that's going to do. Now, the guarantees might just be look at the assembly. That's what it does, right? That's not a pretty useful guarantee, but like there's an intent that volatile should kind of let you know what it's going to do. So let's look at the initial motivation for volatile. And so that was around early Unix times. And there was this example in early Unix using C. Now, just stay quiet. This is not my code, right? But this is early C code. Right? So let's look at what it does. So it has this defined KL to an octal variable. It has 2 structs, not really that important. It has a register variable, which is very quaint. The register variable doesn't have a type, which is great. And then it has a while loop that takes KL, remember the octal address on top, dereferences it because it's a struct and then reads from it. And then it checks that it's greater than or equal to 0 and it spin loops until like it's greater than or equal to 0. And then it sets the value there to something and then it returns RC. Now, ignoring that this is quaint early C code, this is clearly like trying to dereference something that looks like a struct and it's at that octal address. So let's ignore that. Register RC is just quaint, but whatever, it's probably just some value. And so what it's trying to do is it's polling into a hardware thing. In this case, like where you get the characters, right? So it's trying to go get the characters. and just waiting for something to be there. And when there's something there, it returns a value that it read, right? Fairly simple. That's something that you would do in early Unix days. Now, the problem is they wrote this, and then at the time, optimizers were not smart, right? But they tried to be smart, and optimizers started saying like, well, if I've loaded a thing and it hasn't changed because you haven't touched it, then clearly I can just not reload it, right? So it would hoist it out of loop. At the time, optimizers weren't smart. It would be hard to prove that this was actually like an infinite loop or something like that. And people started thinking, well, I want to express to the compiler, like, do it every time I say to do it. Right? Like, do the load every time. Nowadays, compilers are smart. And you could argue a compiler could figure out that this is an infinite loop and you meant to write volatile. But as compilers are smart, like, the basic things are still easy to prove for a compiler nowadays. But as you start getting more and more complicated, if you add stuff to this loop, right, at some point the compiler won't be smart enough, right? So we could try to offer guarantees that, like, if it's a simple enough loop, then we won't like move stuff around to optimize it. But if you fall off this cliff that I can't really define, then we'll start optimizing stuff, right? That's not a useful guarantee for compilers to offer, right? As compiler technology evolves, it gets harder and harder for like actual complex code to not be optimized in the cases you intended for it to not be optimized, right? So I think there's something to be said about the user telling the compiler, hey, like, I have an intent here, right? Maybe volatile is not the right way to express it, but there's an intent. So if you go back and you look at the C programming language, so not the standard, but the book that explains it, it says about this specific example that the purpose of volatile is to force an implementation to suppress optimizations that could otherwise occur, right? So for example, what I explained, a machine with memory map input-output or a pointer to device register might be declared as a pointer to volatile in order to prevent compilers from removing apparently redundant references through the pointer, right? That makes sense. So we go back to the previous example, exactly the same code, and we put this, and then everything's happy, right? That makes sense? The code's still a bit quaint, but like it makes a bit of sense. So there's actually a book that documents the C89 rationale, and I went through it to try to figure out, well, what was the intent of volatile? So here's an example. It says, about the only thing a strictly conforming program can do in a signal handler is to assign a value to a volatile static variable, which can be written uninterruptedly and promptly returned. So who's ever written a signal handler? Yeah, maybe half the room, okay. So who's stuck to this rule? Yeah, I expected that. So volatile is what's like the box that standard conformance is, right? So this is the box that C intended to offer. Now, an implementation can expand that box, right? So for example, POSIX has the concept of signal safety, and there's a handful of C functions that are marked as signal safe. So it expands the box by saying, well, maybe you can store it to a volatile static variable, or you can use one of the POSIX signal safe things. Now, realistically, when you write signal handlers, you still do a few more things, right? So for example, in the LVM, we install signal handlers when we compile. And the reason we install signal handlers is basically two things. One of them is if you hit Control-C, we want to kill the compiler, right? That's one of them. That makes sense, right? So like call exit. It's fine, right? Exit is signal safe. It's good. The other thing that LVM does is it installs signal handler for seg faults and stuff like that. So if the compiler crashes, well, it'll tell you something nice. Now, who's ever crashed Clang? Two-thirds of the room. All right. So you've all seen the error message that gets printed out when you seg fault Clang, right? Yeah. And so that error message is running in a signal handler, right? So what does it do? Well, it captures a backtrace. It tries to generate a reproducer for your problem. So look at your input, so your pre-processed input with all the other files that included and whatever, it'll generate a file with that input. If you're using modules, it'll create a folder. That folder will create all the other things you need for modules. It'll tell you, hey, like the crash log, .crash thing will be over there. How about you go and get it? So it does stuff like that and tells you to file a bug and things like that. Who's filed bugs before on Clang? Half the people who've crashed Clang, come on. We put a signal handler for you. It tells you to file a bug. And it happens that signal handler code was like super broken. It used to be that we would get crash reports from people that like people in my team looked at it. They're like, what is that? So I looked, and the signal handler was crashing while handling the signal to crash this program. That's not good. Right? So there's stuff that you can't do in signal handlers, and it's really a bad idea to do them. So I went up and I cleaned it. I'm still not sure it's correct. It certainly doesn't follow these rules. But that's the intent, right? Volatile was meant to do signal handlers. Okay, so another thing that the designers of C said was volatile doesn't allow caching, they spell it weird, but no caching through this L value. So each operation in the abstract semantics must be performed, right? So in the absence of the volatile qualifier, the content of the designated location may be assumed to be unchanged except for possible aliasing. That kind of makes sense, right? It expresses one of the sentiments about volatile that I had earlier. Another example, a static volatile object is an appropriate model for a memory mapped I/O register. So that's the Unix little carve-out that I had earlier, right? Implementers of C translators, which is a weird way to say compilers, should take into account relevant hardware details on the target system when implementing accesses to volatile objects. It makes sense. Whatever decisions are adopted on such issues must be documented, and volatile access is implementation defined. Right? So there's a list of things you can choose, and you should really document what those are. Who's read their documentation manual for the compiler to see what we're guaranteeing? You have? Does it say anything? Yeah, it doesn't say anything. I mean, the source code is there. That's documentation, right? Like, it's pretty good. Yeah. So another thing, a volatile object is also an appropriate model for a variable shared among multiple processes, right? So if you have a shared memory, which C and C++ don't really say exists, but like you can use volatile and mark that there's an external modification, right? So you're telling the compiler, like, hey, even if you think you see all the code, I've used mmap to talk to another process. The other process is modifying a thing. And so like, don't assume that it hasn't changed, right? So that makes sense, right? It's just like, we don't want to say what shared memory is, but like just slap volatile and it'll be fine. A static const volatile object appropriately models. What does it model? Static const volatile. Stuff that changes constantly. Audio person. Yeah. So a memory mapped input port such as a real-time clock. Nice, nice. Audio people know that, right? Yeah. All right. So a const volatile object models. What does it model? Nothing. Okay. Variables which can be altered by another process, but not this one. All right, cool. If it is necessary to access a non-volatile object using volatile semantics, the technique is cast. Yeah. So cast the address of the object to the appropriate pointer to qualified type. Then dereference that pointer. Now, notice this as one thing. What's the reverse of this? So if it is necessary to access a volatile object using non-volatile semantics, what's the technique? It doesn't say anything. There's no other section that talks about this. Presumably it's not valid. I don't know. The only reliable way to ensure that a local variable retains the value it had at the time of the call to long jump is volatile, not pray, volatile. So long jump is weird because it can return twice, right? And so if you have a variable that's not volatile and then you have long jump, you kind of want that variable to stay, right, to keep its value. And the compiler could effectively kind of try to figure it out. But what you really want to do is slap volatile on there. It's great. Or not use long jump. How about that? Okay, so this is C89 rationale. Now, C++ also has a rationale, believe it or not. So there's a book that Bjarne wrote a while ago called The Design and Evolution of C++ or something like that. And yeah. And there's exactly one section that talks about volatile, one occurrence of the word volatile in the whole design and implementation of C++. Here it is. To match NCC, the volatile modifier was introduced to help optimizer implementers. I am not at all sure that the syntactic parallel with const is warranted by semantic similarities. However, I never had strong feelings about volatile and see no reason to try to improve on the NCC committee's decisions in this area. So a lot of the rationale for C volatile was kept in C++, or all of it, right? And then C++ added const, and people went, well, that's a qualifier too. How about we make it like equivalent? Const and volatile apply at the same places, right? Now, I'll talk a bit more about why that's kind of weird later, right? But basically, what Bjarne is saying here is like, well, volatile and like it makes sense, and we added const, and then like, I don't know, right? Like I don't think people put that much thought into what it actually meant, right? So one thing people agreed on, right? So there's C++, and C++ 11 added the concept of threads, right? And there's a lot of debate leading up to that because POSIX did particular stuff with threads and whatever else. And a lot of people said, just use volatile for like threads and stuff like that. People finally settled on like, no. Volatile is not for atomicity and thread visibility, Right? That's something that most people agree on nowadays, right? But if you go back in like late 90s or 2000s, there was a lot of articles debating this point. So what I want to get into now is like, what does volatile mean normatively, right? So I went into the standards and I tried to figure out what it actually says, right? So that was, everything before was like kind of feelings about volatile. Everything after will be cold, hard truth. Now, it'll still be feelings because you'll be disappointed. Spoiler. All right, so a bit more poetry here. C++ has flaws, but what does that matter when it comes to matters of the heart? We love what we love, and reason does not enter into it. In many ways, unwise love is the truest love. Anyone can love a thing just because, but that's as easy as putting a penny in your pocket. But to love something despite, to know the flaws and love them too, that is rare and pure and perfect. Right? This is about C++, right? Yeah. So, let's start with C++. Intro.abstract. The semantic description in this document defines a parametric, non-deterministic abstract machine. This document places no requirements on the structure of conforming implementations. In particular, they need not copy or emulate the structure of the abstract machine. Rather, conforming implementations are required to emulate only the observable behavior of the abstract machines as explained below. So this is known as the as-if rule, as if I understood what it means, right? So basically what it says is like, well, you write some code and the compiler just does whatever. If you can't tell that it did whatever, right, then as if. Now that it means if you use undefined behavior, yeah, whatever, as if. But there's a carve out to the as if rule. Access through volatile GL values are evaluated strictly according to the rules of the abstract machine. All right, cool, we can get back to like sanity and understanding things. Okay, so reading an object designated by a volatile GL value, modifying an object, calling a library IO function, or calling a function that does any of those operations are all side effects, which are change in the state of execution environment. So that means that like there's all the abstract machine and the compiler can hand wave and do whatever it wants, except with volatile, right? Great. So let's look a bit more at dimensions of volatile. Two accesses of the same object of type volatile sig atomic t do not result in a data race if both occur in the same thread, even if one or more occurs in a signal handler. Okay, so well, but the C rationale told me I could use a static volatile thing in a signal handler. This one says, by omission of other things, that only a volatile sig atomic t is something I can use as a signal handler. That's a bit weird, right? But it's a difference between C and C++, I guess. Artistic changes. Okay, something else. The implementation may assume that any thread will eventually do one of the following: terminate, make a call to a library IO function, perform an access through a volatile GL value, or perform a synchronization operation on atomic operation. So this is the no infinite loop rule, right? So if you write an infinite loop, the compiler does away with it. The reason is because it's applying this to the letter. So if you want it to not eliminate your loop, you could call exit in there, you could like stood out, you could put a volatile thing, or perform a synchronization operation. Now, is relaxed atomic a synchronization operation? Great question. I'll let you read the standard. So the semantics of an access through a volatile GL value are implementation defined. If an attempt is made to access an object defined with a volatile qualified type through the use of a non-volatile GL value, the behavior is undefined. So this one is the reverse of the C one I had earlier. Right? So if you're trying to access a volatile thing without volatile, the standard says it's undefined behavior. Great. Now, this is a great one. You'll love it. It starts like this. I have a quote of the standard with a note. What do notes mean normatively in the C++ standard? Nothing, right. So this is useless. So let's look at what's useless in here. Volatile is a hint to the implementation to avoid aggressive optimizations involving the object because the value of the object might be changed by being undetectable to an implementation. Cool, I'm a compiler implementer. This is a note, whatever. Furthermore, for some implementation, volatile might indicate that special hardware instructions are required to access the object. What do I do with this as a compiler implementer? Nothing. In general, the semantics of volatile are intended to be the same in C++ as they are in C. As we just saw, it's not true because they changed the signal handler stuff. But whatever, it's a note, doesn't really matter. The intent was there. Now I'm being a bit flippant here about like I'm a compiler implementer and I do nothing. It's not actually true. Like I do want to honor what programmers need to do, right? But I do want to remove the sharp edges from C++ and from C, right? So even though it is a note, I do take it to heart, right? And I've done the research, so I'm actually trying. Please believe me. Okay, so a non-static member function may be declared const volatile or const volatile. These CV qualifiers affect the type of this pointer. So this is where C++ took the C stuff with volatile, they added const, and they're like, oh, well, you kind of should be consistent. They're like volatile everywhere, right? Who's had a hard time adding const to functions, and then like it's an explosion, you gotta add const everywhere in your code, right? Not enough hands. I think everyone's done this, right? If you write C++. Now, if you try to be volatile correct, has anyone tried this before? Like instead of const correctness, have volatile correctness? I've tried it a while ago and I just gave up. It was ridiculous. So they also affect the function type of member functions and blah, 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 blah. Okay, cool. So like you can put volatile everywhere to just be consistent with const. Cool. So volatile semantics apply in volatile member functions when accessing the object and its non-static data members, right? So what that means is if you have a class and it's qualified volatile, then like say you have a bunch of ints inside that class, those are all volatile now, right? So you just write your code and unbeknownst to you, the accesses are now volatile, right? So you didn't put volatile in your code all that much, but it's kind of convenient that now it's all volatile anyways. Okay, that's a bit annoying, but whatever. As I was saying earlier, a constructor can be invoked from a const volatile or const volatile object. Const and volatile semantics are not applied on an object under construction. They come into effect when the constructor for the most derived object ends. So this is in class.ctor, and class.dtor has the same wording. Okay, so that like what I said that we felt about C++ actually applies in real life. Parameters declared, declarations that differ only in the presence of absence of const and or volatile are equivalent. That is, the const and volatile type specifiers for each parameter types are ignored when determining which functions is being declared, defined, or called. Right, so I explained earlier, it's actually true. I was not lying to you. Okay, so this is an overload. And it's also in return. I didn't copy paste that stuff, but it says that. So C++ has a bunch of built-in operators, right? So like for all the scalar types, there's like plus and minus, whatever. So here's the list I tried to synthesize of what C++ declares as built-in operators. And you see all the little V's with question mark here? Those are all the things that can be volatile, right? So you can go back to YouTube and like scroll through this if you want all the details, but like this is what can potentially be volatile inside of the built-in operators. All right, there's more volatile in C++. Last I checked, the C++ 17 draft, I think, or standard, had 322 instances of volatile inside of it, right? Which is kind of good for like a 2,000-page document, right? So more instances of volatile, this time in a library. Tuple has volatile things. Tuple size and tuple element can be volatile. Why? I don't know. Variant has the same thing. Variant size and variant alternative can be volatile. Why? I don't know. Right? So we made the mistake of making volatile super consistent with constant whatever, and someone went and tried to make those two classes like volatile correct, right? And like I don't know. This is a bad idea. Another one that I mark it as a quote, but I'm not actually quoting the standard here. Atomic goes and says volatile overloads for all the things. Right? So every single thing in Atomic can be volatile. Mostly every single thing. And at that point, I just didn't want to copy paste this stuff, so I was just like, whatever. It's like all this stuff is volatile. Okay. So this is what the standard says, right? Now, what do compilers do with this, right? So compilers aren't just like mean black boxes that mess with your code. We actually try to follow rules, right? Like we try really, really hard to follow these rules. Now, I work on Clang and LLVM, so when I say what do compilers do, I really just mean what does Clang do, because I'm not going to go and document the other stuff, right? Like I did that kind of in my previous talk. You can go read the documentation, it has Billy over there. So what does LLVM say about volatile? Well, LLVM has a language reference. It's actually quite good and quite readable. And it says certain memory accesses such as load, store, and LLVM.memcopy may be marked as volatile. Now, it means that every single IR operation that touches memory, you can also put volatile in it. If you do like -emit LLVM on mat.org, Gabble, you can see that it'll slap volatile before load or store whenever you do that. So the IR contains the information that stuff is volatile. So it's no longer the type that's volatile once you load LLVM IR, it's the instruction that's volatile when you load LLVM IR. And this LLVM.memcopy thing, there's a bunch of built-ins that touch memory. All of those can be volatile. How do you access them from C or C++? I won't tell you. But there is no way in C and C++ to write a volatile memcopy in conformance standard C or C++. LLVM has it. It's just a secret. Okay. The optimizer must not change the number of volatile operations or change their order of execution related to volatile operations. So when we move stuff, we have a bunch of code, like in whatever reorders instructions, it says, is this volatile? Actually, I'm lying. It doesn't say, is this volatile? Because their IR instructions have a .isVolatile member function, and they have a .isAtomic member function. Now, what code usually does in the optimizer is it says .isSimple. And if it says, if not is simple, just bail, don't touch anything, right? So anything that's atomic or volatile, most of the time, we just don't really touch. Now, as stuff evolves, and some people really want to optimize atomic code, atomics are starting to get optimized. But basically right now, LVM tries to not touch anything if it's not simple, right? So just write simple code and you'll be good. The optimizer may change the order of volatile operations related to non-volatile operations. So I talked about this a bit earlier. So if you have volatile and non-volatile stuff, they may kind of move around each other. In which ways, the manual does not say. But it's well documented in the source code. Okay, it also says that a volatile loader store may have additional target-specific semantics, right? So this makes a lot of sense. That's what the C and C++ standards say, and that was the intent, right? So like if you're ARM or Intel or whatever, and your hardware has specific like MMIO or whatever registers, like you can give meaning to those things, right? That's what the compiler says. Right, so it explicitly says if you're writing a backend, do give semantics to stuff. Any volatile operation can have side effects, and any volatile operation can read or modify state which is not accessible via regular load or store in this module. Volatile operations may use addresses which do not point to memory, like MMIO registers. Right, so just kind of writing down in the language reference what the standard says as well. The compiler may assume execution will continue after a volatile operation. Right, so the same way, dereferencing like a null pointer is UB, and so the compiler can assume this never happens. And so if you write a explicit dereference of a null pointer, the compiler just assumes that won't happen, and it might just like continue executing. It'll say, surely you do not mean to execute UB. I'll just do away with this thing. The same thing applies for volatile, at least within the LVM optimizer. Operations which modify memory or may have undefined behavior can be hoisted past a volatile operation. That's the implication of this, right? So it's not just because we want to be assholes to you and like remove your undefined behavior. It's because the optimizer actually gets a lot of mileage out of being able to be an asshole to your code. Now, you could go in LVM and remove that part of the code that does this and see what the difference is. There is actually a difference if you have volatile code in there. Another quote here from the LVM reference. IR level volatile loaders and stores cannot safely be optimized into memcopy or memmove intrinsics, even when those intrinsics are flagged as volatile. Right? So what it means is you can't just like make it a memcopy if the original code did not have a memcopy in there. Likewise, the backend should never split or merge target legal volatile loads and store instructions. Right? So that's putting into langref law what was already in the standard. Okay, so a little diversion from here. It's one of my favorite jokes. How do you know if a C++ developer is qualified? I know. You know, yeah.
Look at their CV.
You look at their CV, thank you. Right, so it's great, thank you. It's my favorite C++ joke, it's good. Everyone groans when I say it. It's amazing. So, this is what compilers said, and this is what I said on Twitter. Now, we'll look at what we're trying to change to make volatile safer. So, there are three things that all wise programmers fear. C's corner cases, hardware platforms with no documentation, and the anger of an optimizing compiler, right? So my goal here is not to add some fear to your heart when you write C or C++ code. My goal here is to remove the corner cases while still allowing you to express what you need to express with volatile. I would argue that we could have better tools in the standard to express what you mean, because as we saw, volatile means many, many things in different contexts. Right? So you could be able to express to the compiler exactly what you mean. I haven't figured out what that is precisely, right? So what I'm trying to do here is remove sharp edges, eventually like remove a bunch of stuff, give you better tools, and then later on remove the rest of volatile, right? But I'm not sure that's doable, right? So I want to make sure that like you don't fear stuff more than you already do with respect to volatile. I'm not trying to make you afraid of stuff. Okay, so when I set out to do this in the original paper, I had 7 goals that I listed in the paper. First one was do not break good code, right? Not that volatile is good code, right? But like it works, it follows the letter of the law, therefore I'll call it good, right? So my goal was really continue supporting the time-honored usage of Volatile to load and store variables that are used for shared memory, signal handling, set jump, long jump, or as other external modifications such as special hardware support, right? That was one of my goals, okay? And some of this made it to C++20. Did I succeed in this goal? I would say I have, because I haven't touched any of this stuff, right? Success. Goal number 2. Remove confusion. So deprecate and eventually remove volatile compound assignments such as like plus equal and stuff like that, pre and post increment and decrement, right? Because as I showed earlier, I don't really know what that means. Did I succeed in this? Yes, this will be gone from C++20. Goal number 3, remove useless abstractions, right? So I talked a bunch about how volatile was put in place in C++ to be consistent with const. And I wanted to look at, can I deprecate and eventually remove volatile qualification of member functions? So not change qualification of data members, but just member functions. Did I succeed in this? Well, no. I think it's too ambitious to change all of this stuff at once, right? And we don't really have a replacement for volatile. And there are arguably some amount of code that use this in a correct way. So I didn't want to like rock the boat too much. I still think this is something we want to do, but not in 20. First, because it's too late to do in 20, but also because like we need to think about it a bit more, right? But I wanted to plant that seed with the committee and with you all today and you on YouTube to make that change eventually, right? So I don't know what it'll look like, but I want to talk about it. Next thing, I want to remove complexity from the language. So I want to deprecate and eventually remove partial template specializations involving volatile, overloads on volatile, and qualified members functions for all but the atomic and numeric limits part of the library. That's a mouthful. Basically, I'm saying, well, like in the library, we've tried to be volatile correct. It's a bad idea. Let's just do away with it. Did I succeed in that? Yes. It turns out that only tuple and variant really needed to get any surgery done, and it's only 4 member functions for each. Wasn't that hard. Okay, goal number 5, make volatile useful. So deprecate and eventually remove volatile member functions of atomic in favor of new template partial specializations, which will only declare load store and only exist when is always lock free is true. Preserve most volatile free member function overloads for atomic. What does that mean? Well, as I explained earlier, atomic really means like there will be no tearing and there's synchronization involved, right? Volatile really means I'm doing something special, don't optimize too much, it's okay if you tear. Now volatile atomic together seems like it doesn't make sense, but it actually does, right? What you're saying is I want this to be observable between threads, have some ordering between threads. I want it not to tear, but also I'm doing something tricky, so don't optimize my atomics away. Like don't assume anything. Maybe between me and the platform, there's a contract where like using comp exchange makes sense, right? Stuff like that. Like maybe the platform gives me guarantees with respect to volatile atomics. Right, so there is something to be said about volatile atomic making sense. Now it's really like a niche use case, but I don't want to break it. Right now, at the same time, non-lock-free atomics, right? So the ones where you can have instructions that tear or where you acquire a lock or something like that, it really doesn't make sense to make them volatile, right? Like this is nonsense, right? So what I'm trying to do here is I'm saying, well, if the compiler does not know that this atomic instruction is always lock-free, then it won't know which instructions to emit. Right, it'll emit instructions that can tear and whatever else. This is probably a bug in your code, right? I want to do away with it. If this, in your implementation, I haven't heard this from anyone, but if this in your implementation actually meant something, maybe you want to be writing assembly, right? Like as a compiler writer, I don't know what to do with it. And I haven't heard from anyone that you wanted to do this, right? But there are reasons sometimes when you want to drop down to assembly. This is one of them, right? So what I did is I went and the standard said like volatile all the things for atomic. I went in and I kept the volatile all the things, but I added a mandates clause that says is always lock free. What does that mean? Well, it's you like have a spinne or a concept or something like that for the implementation. Just hand wave, and if you try to instantiate it, it should just give you a compiler warning, right? That's what that effectively means. So the standard already says volatile all the things. I said mandate all the things as well, right? Make sense? Did we succeed in that? Yes. Okay. Next goal I had, remove truly useless stuff, right? So I wanted to deprecate and eventually remove non-reference and non-pointer volatile parameters. So deprecate and eventually remove consts as well as volatile return values, references and pointer to volatile remain valid. So that's the example I had earlier. Did I succeed in this? I'll say I did, right? But I didn't touch const, right? So const is still nonsense as a top-level qualifier for parameters and for return values. People weren't really comfortable removing const, so I was like, I don't really care that much. And so now I've added inconsistency to C++, and I think that's beautiful, right? Like we understand the flaws and we love them, right? So if you want to be asked to your coworkers, you can go and put consts and parameters and return values and say, what does that mean? Don't do that, okay? But it's beautiful. Like, you're like, this doesn't make any sense. Great, all right. Last goal I had was to create a better tool. So we have a paper, 1382, me and Paul McKinney over there, with volatile load and volatile store. So what we're thinking of doing is, instead of expressing volatility as a property of the type, right? You can qualify things as volatile. We want to express it as a property of the instruction stream. And that makes, in our minds, a lot more sense. Now, that's what LVMR does, right? And qualifying something as volatile or not doesn't really make sense. Like, when you have a class that represents hardware, right? Do you instantiate it both as volatile and non-volatile? No, right? Like, you created a useless abstraction through this type by allowing it to not be volatile. It doesn't make sense. Really what you're doing is you're accessing things as volatile and non-volatile. So the instruction is what you want to do here, right? Now, maybe it makes sense to have a qualifier that says, when you access this, always use volatile load and store, right? Maybe that's what we need to have, but really, like, the fact that the code doesn't scream, I'm doing something volatile, is really troubling to me, because I've seen bugs where that's exactly what's going on, and you think you're interacting with the hardware, and in fact, the compiler might make you interact with the hardware because it emits an instruction, because it couldn't prove that the instruction was useless, but next release to the compiler does away with the instruction, because now it can prove that your access is useless, right? So it's a big gotcha that in code readability, when it doesn't look like a volatile access. And having function templates, volatile load and volatile store, would save that, would fix that. And so Paul works on the Linux kernel, and that's effectively what Linux does, both for volatile and atomic, right? So Paul has a paper that describes the memory model of the Linux kernel, and they don't deal with types as being volatile or atomic, they deal with instructions as being volatile and atomic, and that works really well for them. So that's the goal. If you read the current paper, it doesn't really meet that goal. In fact, we presented it to SG1, the concurrency and parallelism subgroup of C++, and it got like a lot of shoot downs, but for valid reasons, right? It's like we tried to design a thing and it's not quite what people wanted, so we're going to come back with a better approach to this. But we're trying, right? That's one of the things that we want to do. So that's not done yet. Maybe in 23, maybe 26. I don't know. That's one of the goals. Now, bonus goal. One thing I hadn't thought about when I was writing the paper that's kind of dead obvious in retrospect was, hey, structured bindings. So deprecate and eventually remove structured bindings, which introduce volatile qualified identifiers. So does everyone know what a structured binding is? When you have the square brackets and you destructure a thing, whatever. Does that copy things? Does it create a reference? Does it no, it doesn't, right? It just gives it a new name. So if you try to capture a volatile thing in a structured binding, you can put const on it, for example, to say I'm pointing at that thing, but it's not like don't let me modify it or something like that. But it doesn't create a copy, and so when you put volatile in there, there's kind of an implicit volatile when you capture a structured binding that's volatile. And again, I think that's a useless abstraction. It's a pitfall in your code that you probably did not intend. And so as I was doing stuff, people pointed out to me, oh, you forgot to do structured bindings. You mean to do that. And I was like, oh, maybe I should do that too. So that's also in C++ 20, that change. It wasn't one of the original goals, but it's a goal I did achieve inadvertently. So final paper for C++ 20, there's now two papers, one for language, 1152R4, and one for library. I had to split them up because the committee's really, really busy, especially the library side. So the first language paper is coming to C++ 20. The second library paper is probably also coming to C++ 20, but it's just a procedural thing to split it up and then get a national body comment version or something like that. If you're a national body and you can comment on it, please do. 1831R0. Yeah. C++ works weird sometimes, but it's fine. Okay, so a few examples of what I mean here. And when I say examples, I don't just mean I gave you examples earlier and it had kind of boring variable names or whatever. These examples, unless someone from the committee, one of the editors, changes their mind, these examples will be in an ISO standard. So ISO C++ 20 will have these examples. Ready for it? This example. Volatile int velociraptor plus velociraptor. Is this a single memory operation, 2, or a 6-foot turkey? I don't know. Jurassic Park, anyone? Yeah. All right, so a little dinosaur reference. This is beautiful.
Are the comments in the standard?
Yes, this is literally in C++ 20. under heading deper.volatile. The pull request is still out because procedural stuff, but they asked me to put examples in the standard. If you ask me to put an example in the standard, you will get My Little Pony references as you did in C++ 17, and Batman references, and dinosaur references. That's what I do. This whole thing was to get dinosaurs into the standard, come on. It's not true, come on. Okay, so next thing. This is another example that's also in the standard. I don't know what happened. Like, I don't do drugs, but like, this is in the standard, or going to be in the standard. They asked me to clarify stuff and be like, is that okay? Is that not okay? Because like the standard's not a manual, but you kind of want to explain to people like, okay, this is deprecated, but here's what it does, right? And so brachiosaurus have tails and necks, and I don't know. This is in the standard. Nice. I didn't put the Unicode thing in there because I don't think the standard does really well with Unicode. Maybe I should. I don't know. You can send pull requests to the standard, by the way. Don't do it, but you can. GitHub.com/C++ spelled out /draft. Don't do it. This is what happens when you do it. Okay, next one. Struct Amber Jurassic. I explained all of this, but this is in the standard. It's beautiful. So another dinosaur reference. It's great. Last example that's going to be in the standard is a structured binding one. So if you had no idea what I was talking about with structured bindings, this is what I meant. It's also in the standard. I had to look it up because I don't know dinosaurs that well. My kid's not old enough to be into dinosaurs yet. He thinks lizards are dinosaurs, not ostriches, which are. But so Alvarezauroid, whatever is that a disease? It's a dinosaur, and they have 4 limbs and stuff, so it's good. So this is also in the standard. All right. So this is the end of the talk. Thank you. We've got 3 minutes for questions. It's probably better if we take it outside unless it's a really short questions. Please don't say question, more of a comment than a question. We can do that outside.
I'd like to follow up on the Lord store and volatile Lord and volatile store suggestions you had in the end. What's your answer to overlaying C++ structures on top of MMIO registers?
Right, so when you overlay C++ structures on MMIO, usually the manual says, here's the struct, and here's literally the code you write. And my hope is that the compiler that you use with your target actually agrees to that. So it's basically the hardware manual is offering you a guarantee that's probably been vetted by the compiler that comes with it. Right? And so specifically, there's some on ARM, some ARM chips, there's ways to access bit level things that are volatile. That's one of the things that's there. And I haven't done that much programming where that was the case, right? So I really have to go and look more at that. One of the things I had thought about was deprecating volatile bit fields, and I realized it was actually a thing that was used pervasively. So I want to do a bigger survey of what people do, but that type of low-level hardware stuff is kind of hard to come by. Unless I buy the hardware, I don't get the manual. And so I'm kind of missing examples of where the line is and what we want to allow or not allow, right? So I think it's a thing that's fine. I think it's a good abstraction to have a struct and then maybe methods to access the stuff underneath, so you don't need to think about your accesses and whatever. So just describe what you're doing. But I don't think I want to deprecate the whole thing as is, but yeah, I'm not sure what the right solution is for
that. Correct me if I'm wrong. On slide probably 75, you said that you failed in deprecating the volatile qualification of member functions, correct? Right. And probably slide 56 said that volatile qualification interprets the whole instance as a volatile. Does it mean that alignment gaps between the member variables also treated as volatile?
So alignment is tricky. So the padding between types and whatever is tricky, and compilers don't necessarily do the right thing with that. There's actually a bug in Clang right now where we don't do the right thing with padding. So I don't think there's a really good answer. Me and Michael Spencer over there actually fixed something with when you have a atomic with a struct and the struct has padding inside of it, or say you had an int that had padding, which doesn't actually exist, but say you had that, then right now, comp exchange doesn't say that this can work, right? So there's no guarantee before C++20 that comp exchanging something with padding will ever work, right? So the padding might change because the way it's specified, you get a non-atomic thing, and that can change the padding every time. So even though you try to do the store, the padding value might be different. And so in C++20, we strengthened atomic with respect to the padding, but we haven't done anything with volatile. I think it's kind of nonsense, but
So if assigning or copying instances with padding happens, then the behavior is not guaranteed to be correct.
I believe that's correct, because padding is not an actual member of the thing. Now, there are guarantees about the value of padding coming from C if you like put curly brace, 0 curly brace. So if you initialize none of the members, the padding is indeterminate. If you initialize, I think, all of them, they're determined. But if you initialize a subset of them, the padding is guaranteed to be 0 or something like that. So C says some really weird stuff. And there are guarantees with padding, but when you copy it, it's not guaranteed to be copied. Now for volatile...
But the members themselves guaranteed to be copied correctly. Okay,
yeah.
Thanks.
But the padding, I don't know. All right. Thank you, everyone.